Thanks for the introduction, and good morning, everyone. Thanks for attending my presentation. This is a joint work with people from TII, Technology Innovation Institute, and in particular, Anna, the main author, who could not be here to present today, so you'll have to do with me instead. And this paper is trying to answer the question of, given a set of sequences of bits, can we determine whether they look random or not? And if we can we explain why we think they are not random, and do that in an automatic way if possible? So to start this presentation, we will talk a bit about deep learning and automated tests in cryptanalysis, which is the field that we focused on. And then we will present our solution, NNBits, which uses machine learning to do these distinguishing tasks, and in particular by trying to predict some of the bits of the sequences. And we'll talk a bit about that later. And then we will present one application of this system. And I was informed that I have a bit more time than expected, so if there is any question during the talk, if something is unclear, please feel free to interrupt me and ask, and hopefully we can keep everyone on board. So the main context of this work is the context of distinguishers in cryptanalysis, where we are trying to determine whether a cryptographic primitive behaves as its random equivalent or not. And in particular, in this talk, we are talking about block ciphers, which are primitives that take as input a plain text and a key, and encrypt a message, encrypt the plain text to a ciphertext that hopefully looks random if you don't know the key, but if you know the key, you can retrieve the plain text from this ciphertext. And to evaluate whether a block cipher is secure or not, there are two main approaches, and the first one is the golden standard, of course, and it's cryptanalysis, which you are probably very familiar with. And here we have human cryptographers, sometimes assisted by automated tools, that really look into the details of a primitive. So look at all the components and try to find loopholes, weaknesses. And that's a very long process, typically. So for instance, we have the AES, Advanced Encryption Standard, that has been standardized over 20 years ago. And we still regularly see new cryptanalysis papers on the AES. So this is something that basically never ends unless the cipher is fully broken, I guess. On the other side, we have automated techniques, which are way weaker because there is not such a dedicated analysis by experts, but that hopefully provides an answer as fast as possible. And in this case, in the case of automatic techniques, we are looking at the cipher as a black box primitive. So instead of looking at the internals of the cipher, we look at the inputs and the outputs and see if we can distinguish some property. And in particular, we have the example of the NIST statistical test suite, STS, that was used against all the candidates for standardization during the AES process. And it's a battery of statistical tests that look at a data set generated from the cipher, so sequences of bits, and try to determine if there is some non-random property that appears. One limitation of that is that you can basically define an infinity of randomness tests. You can define a statistical test that look at each possible non-random pattern. And for this reason, no test suite can be fully complete. So with this work, we attempt to do something that is a bit more generic. So instead of designing thousands of tests, for instance, the NIST STS is composed of 189 tests. We are trying to have something that is a bit more generic, and that works. So this system that we built is based on deep learning. And deep learning, as you may know, is very strong at detecting patterns. And this is exactly what we want to do, right? We have a sequence of bits that has some non-random patterns that we want to find. And so that is exactly the ballpark of deep learning. So deep learning is very strong at finding patterns. So for instance, if you look at image classification, you can have a deep learning algorithm that you train at recognizing images of cat and dog and labeling this data, either cat or dog, and so that it generalizes to new unseen data. So, of course, we have seen in the recent years that machine learning algorithms are able to reach superhuman performances in a wide variety of domains. In particular, for instance, the game of Go or chess, more recently ChatGPT, that kind of things. And so the question is how can we apply this to cryptanalysis? There was an answer, part of an answer that was provided by a paper at Crypto 2019 by Gore that for the first time used a deep neural network to perform cryptanalysis of a block cipher better than human cryptanalysts. And that was the block cipher spec. And here, what was done is differential cryptanalysis. So basically, there was one neural network, so machine learning algorithm, that was trained to distinguish, given two ciphertexts, whether they were two random ciphertexts or they were the ciphertext corresponding to the encryption of a plaintext P and another plaintext P XOR delta for delta a fixed difference. And what was very impressive with this work is that for 5, 6, 7, 8 rounds of spec, the neural network was able to distinguish a single pair of ciphertexts with a high accuracy. Now, why such a high accuracy could be reached is a very difficult question. And in particular, with some people from NTU in 2021, we tried to explain what Gore's neural distinguisher could learn. And it took us quite a while to think of something that partially explains it, but it is still an open problem. And that brings us to the second point that we want to address in our work, which is explainability. It's something that is a big open problem in AI. It's easy to train-ish to train something that is superhuman at whatever field you want, but it is very difficult to explain why it is so good. And in our system, we wanted to embed this explainability directly within the training process. So what we propose is called NN bits, which aims at pinpointing weak bits in a given pseudo-random bit sequence. Okay, so if you look at Gore's neural distinguishers, it was receiving pairs of ciphertext that were either random or corresponding to a certain distribution, and it was trying to label random or non-random. Here we do something different. Instead of directly labeling as random or not random, we have our sequence that is all issued from the same pseudo-random generator, so we don't have random sample in the data set. And we try to predict different bits from this sequence. So here we have an illustration on our system. We have a data set here on the left. We have sequences that are n bits long, and we have x of them. So we have a set of sequences produced by some pseudo-random generator. And to analyze them, we use an ensemble of big N neural networks. So what is this ensemble? It's a set of neural networks that share the same architecture. So they are built in the same way, but the data they receive is different. And for each neural network, we have this data set that comes in, but with some bits, the bits that are represented in blue here, that are set to 0. So basically, it's given a partial data set where some of the bits are missing, and then each neural network tries to predict these missing bits, okay? And so with that, we train all our neural networks, and each one is trying to predict some different set of missing bits. And in the end, we compile the results, and we can see which bits are easier to predict than others. So just to make it clear, so this is trained on a training data set. So we have this a set of data for training where we try to teach the neural network how to predict these missing bits. And then this part is done on a testing data set where we have our trained neural networks, and then we give it new data, and we see how good it can predict some of the bits. So here, why is it relevant for distinguishing? Well, if we have a data set that is truly random, then there should be absolutely no dependencies between the bits. Okay, so if you have all the bits of the input minus one position, then you should not be able to learn anything about that missing position, and you should not be able to predict it. On the other hand, if the data is not fully random, and if there are some weaknesses and some dependencies between the bits, then you can do something that is a bit better than 50% prediction accuracy. So that is the main reasoning behind our architecture and n-bits. And now you may wonder what data set we used. For the data set, we used what is called the avalanche dataset, and in particular the plaintext avalanche dataset that was used that was used for the NIST statistical tests in particular. And it's based on the notion that if you have a function that is supposed to behave randomly, then if you change one of the bits of its input, you are hoping that on average, half the bits of the output will change, right? Because otherwise there is some non-random property that you can detect. So in the creation of this avalanche dataset, we start with a plaintext P that we choose at random, that is n bits. We encrypt it with a key K that is here all zeros, and we obtain an n-bit ciphertext. So that is our basic data block. And then for each position, each of the n-bit positions in the input, we generate a new plaintext that is this initial plaintext with one bit flipped. Okay, bit I is flipped, and then we encrypt it again. We get a ciphertext. And we XOR this ciphertext with the initial ciphertext C. That gives us one block, block I, corresponding to one input bit flipped in position I. Okay? And so, as an example, in Gore's neural distinguisher, the input difference that was fed to the neural network was a single bit input difference, and so it would be somewhere around here. So that is something that appears in the data set, and that will be interesting for later. So once we have all these blocks, then we concatenate them into what we call a plaintext avalanche sequence. So we generate one of these plaintext avalanche units, which is n blocks, n times n bits, sorry. And then we concatenate them into 1 million bit sequences, and we get 300 of these sequences. And that is mirroring the choices that were made by NIST in the STS experiments and the AES candidates. Now, with this data set, we tried comparing it to the result of the NIST statistical tests. And here on this table, you have on the left the results obtained by the NIST STS. And this result tells from which round the primitive is deemed to be random. So as you know, block ciphers are primitives that use a simple round function that is iterated many times. And so here, for instance, we have that for AES, after 3 rounds, the NIST STS tests, the statistical tests, are not able to detect any non-random property. And so in addition to testing AES, because, well, it's AES and you kind of have to do it, we also tested a much more recent cipher, which is the block cipher spec, which comes in different sizes, which was very nice to test the scalability of our system. And here we see in the column S1 that the NN bits experiment that I presented was able to detect a non-random property further than the statistical test. So for instance, for 7 rounds of spec 32, it was able to find non-random properties, whereas NIST STS was stuck from 6 rounds. Okay. And so this is the experiments run using the n-bit system. And then we have another set of experiments that we call S2. And here I won't go into the details, but this is a different setting. So instead of trying to predict specific bits of the sequence and making a conclusion on randomness based on that, we have direct labels that say random or not random, and we try to predict the labels. Okay? So this is able to reach more rounds, but it uses a lot more data. And more importantly, it does not have a property that we wanted, that is explainability. So when I talk about explainabilities for n-bits, what do I mean? Here we have an illustration of what happens when you run n bits for 1 round, 2 rounds, 3 rounds, 4 rounds, 5 rounds, 6 rounds, 7 rounds of spec 32. Okay? On the avalanche dataset that I showed earlier. And we see that after 1 round, there are a lot of bits that can be predicted with probability 1, with 100% accuracy. So here on the x-axis, we have the bits. So remember that the 32 first bits correspond to 1 bit of the input flipped, the first bit of the input. Then the next 32 bits, the second bit of the input flipped, and so on. And here we see that as we progress through the rounds, it becomes more and more difficult to predict bits. And from round 6, there is only a little bit here of the data that seems to be predictable. And for 7 rounds, we only have a tiny speck here that appears to be not random. So if we zoom on this tiny speck, we see that it's actually bit 716 and bit 732 of the avalanche dataset, which probably does not tell you much right now. But if you look at the position of these bits, they actually correspond to the difference that was used by Gore in his neural distinguishers, so which is hexadecimal 400,000. And it means that basically NN-bits was able to identify that if you have a given input difference, this one that was used for neural distinguishers, you have some non-random properties up to round 7, and that this is supposedly the best input difference that you can use for this type of experiments. And even further than that, in terms of explainability, we can also detect dependencies between bits. And here, what I mean by that is that on the left, we have the number of networks that predict this bit 732 with a given accuracy. And we can see that there seems to be two different patterns here, right? And if we look at it a bit more closely, we see that there are two distinct cases. So in one case, we have bit 716 that is not present. When I say it's not present, remember that in NN bits, we remove some of the bits of the input and we try to predict them. Okay, so if bit 716 was removed from the input, then we cannot predict bit 732 with a good accuracy. But if bit 716 is present, then bit 732 becomes easy to predict. And this, we probably won't have time to go into the details, but if you're familiar with the block cipher spec, it's a phenomenon that you can explain, because the XOR of these two bits gives you 1 bit of the difference at round 6, and this bit happens to be biased. So that's something that I found very interesting to look at. Now, after all these explanations, you're probably burning to play with this system, and you can do so because the source code is public. It is here. And the first step that you will probably want to do is try it on your own data sets. So if you have data sets that are pseudo-random and you want to look for weaknesses or for bit patterns that can be identified, you can add your own generators to Avalanche dataset generators, following the templates that we have. And then everything you need is in the Demo1 notebook that was prepared by Anna and that is super complete. So hopefully it is super easy to reproduce these experiments with any dataset generator of your choice. And then if you want to go further and look at all the experiments that I did not present in this talk, the Demo2 notebook is there, and it is as well very well documented, so hopefully it should be easy to use. Now, in conclusion, what we did with NN-bits was on one side, we were able to identify the input difference used in neural distinguishers. We were able to retrieve it from the Avalanche dataset, which was quite interesting, as well as identifying some patterns, such as the pattern of the mixed-colon operation in AES in round 2. They all appear in this explainable part. And also, we were able to provide some understanding of Gore's neural networks. And yeah, so in summary, we have a system that is able to look at a pseudo-random data set and provide bit profiles, which bits are easy to predict and which ones are not, based on something that is way more generic than statistical tests, because we just have a one-size-fits-all neural network. And one interesting thing that could be looked at in the future is trying it with different types of neural networks, because at the moment in the paper, what we use is a generalized version of Gore's neural distinguisher, but you can plug in pretty much any neural network in the ensemble and see what it looks like. With that, I will conclude my talk. Thank you for your attention, and I'll now answer questions.
Hi, thanks for the talk. Could you put this distinguisher into perspective? So if I can predict bit 732 of the 7th round of spec with 50.2% accuracy, how does that translate to like the cost of a total key recovery of spec or a round reduced spec or something?
So in practice, that would not lead to direct attacks. I think the main point here is to tell the cryptographer where to look. If you look, for instance, at Gore's paper that used this input difference and that could retrieve that these bits were weak, Based on this paper, there was another paper by Biryukov, I think last year, called Meet in the Filter attack or something, where he uses the fact that this particular part of the space has some weaknesses and builds new cryptographic attacks. So I think that's the main interest, more find where there is something to look at, and then we can look at this place.
Is there any other questions in the audience?
Thank you very much for the talk. So do you think UH2 is also applicable for the random number test instead of this random number test?
For what test, sorry?
So the UH2, is it possible for the random number test?
Mm-hmm. Instead of block ciphers, you mean?
Yeah, so instead of the attack detecting the cryptanalysis, so just use for a random number test.
Yeah, it could be adapted. So if you want to try it, actually, you can, or we can talk about it a bit more. But you can go to the source code and directly plug in your generator, whatever type of generator in this folder, and normally everything runs automatically.
Okay, thank you.
All right, thank you, David. I'm going to go ahead and queue up the next part of the pre-recorded video for our second speaker. Thank you again.
Good morning, everyone. It's an honor for me to present our paper today. Our paper, Improved Heuristics for Low Latency Imitation of Linear Layers, is a joint effort between Zheng Zhao and Meiqing Wang. Our presentation is only for educational purpose. Let's start by discussing some background information. Firstly, I have a question for you. How to apply ciphers to results-constrained devices? Yeah, that's why we're interested in the lightweight cryptography. In recent years, lightweight cryptography has become a major focus in the cryptography community due to the rapid development of lightweight communications, such as the Internet of Things and radio frequency identification tags. These devices have limited resources in terms of circuit size, the power consumption, and the latency. Therefore, we need to expand the cryptography applications to these devices. Generally speaking, research on lightweight cryptography has been divided into two directions. The first direction is designing new lightweight symmetric key primitives that are efficient in either hardware or software implementations. The second direction involves optimizing existing implementations of a given cipher, which can aid in designing new lightweight ciphers. The limitation criteria include power, energy, throughput, the area, and the latency. In practice, the diffusion and confusion components are relevant to linear and nonlinear operations. In this paper, our work mainly focuses on the area and latency, that is, the matrix used in the mixed columns like AES. Our team has been working on obtaining AES in hardware circuits, which requires a deep understanding of the round function and linear layer. We can consider the AES round function. Optimizing the limitation of the linear layer will lead to significant improvements in the area of the hardware circuits. To illustrate this point, we show the example. Let's take this 3 × 5 matrix as the example. its Hamming weight is 11, and the row number is 3. The first line is Y0, the second line is Y1, the third line is Y2. Then, a trivial circuit for this matrix requires 8 XOR gates. Suppose one XOR gate needs 2 GE. The circuit requires 16 GE. However, after our optimization method, the new circuit only requires 4 XOR gates and half the number of the GE. This example demonstrates that by optimizing the limitation of the linear layer, we can reduce the area of the hardware circuit required. Then we show the depth of the circuit. The depth is not defined as the maximum number of XOR operations of a path in the circuit. For the optimized circuit, we need to consider how to implement it. If we apply XOR gates in order, that is, we first implement x3 plus x4, then implement x1 plus x3. The depth of the circuit is 4. So if you want to generate a circuit with a minimum depth, we need to restrict the order of certain operations. We show an ignition with only depth 3. It applies 2 XOR gates in the same depth. Next, we provide some new aspects for SLP problem. The shortest linear program problem is defined as finding a solution with a minimum number of XORs to compute the multiplication of a constant matrix. The SLP problem has applications in various fields, such as optimization, computational geometry, and operations research. It is a well-studied problem in the field of theoretical computer science and has been shown to be NP-hard, which means that it is unlikely to have an efficient algorithm to solve it exactly for large instances. However, there exist various approximation algorithms that can find a solution that is guaranteed to be close to the optimal solution. The SLP problem focuses on minimum XOR counts, whereas we are also concerned with the area and latency of a circuit. So we extend the definition of SLP problem. For the SLP-A problem, we are concerned about the area instead of the XORs. For the SLP-D problem, we are concerned about the XORs with a depth limitation. We need to emphasize that under depth constraints, the circuit behaves differently. There are 2 heuristic algorithms for solve the SLP-D problem. The first method is the forward search. The second method is the backward search. Their difference is how to generate the circuit. The forward search and the backward search are both search algorithms used to find the paths or sequences to solve the problem. For forward search starts from the start point and gradually expands the path until the end point is found, while backward search starts from the end point and generally expands the path until the start point is found. The forward search uses the depth first or breadth first search strategy, while backward search usually uses the depth first search strategy. We first introduce the forward search for SLP-D problem. First, It treats the input nodes as the base set. Then it executes the following steps iteratively. It chooses the combination and adds it into the base set. If every node is added into the base set, we'll find the proper circuit. How to choose the combination is based on the following three rules. These rules rely on the dist set. The dist set keeps track of the distances of each output value from the base set. We can see the example. The matrix is shown and the imitation is listed in the table. The imitation is generated by the BP algorithm with the depth limitation. It requires 7 XORs. However, we observe that the next candidate for the heuristic algorithm is usually dependent on the output set, which means that the results are relevant to specific output sets. We propose the division optimization technique. It splits the output set to many sets. Suppose that we split the output set into 2 sets. The first set includes Y2, Y3, and Y4. The second set includes Y0 and Y1. Then we can generate 2 circuits. These 2 circuits can be combined to the final circuit. The new circuit only requires 6 XORs. And for the backward search, we also find some properties. We first introduce a search. For solving the second problem, it defined 2 sets. The first is the working set. The working set contains the nodes that we need to split. The predecessor set contains the nodes that we do not split in this state. Note that the nodes in the predecessor set can be reused. Then we can see that given circuit, we can always find a graph from the target nodes to all the unit nodes. Because the framework in right can ensure that the output has a minimum depth. For the given matrix, the working set contains all the target sets. Then we split the nodes in the working set iteratively until the working set is empty. Next, we split all the predecessor nodes. We repeat the procedures until the working set only contains the unit nodes. It means that we finish the split process. The example shows the procedures. The depth of the working set is decreased from 3 to 0. Each time we pull the nodes from the predecessor sets into the working set, the depth decreases by 1. When the depth of the working set is 0, this means the working set only contains the unit nodes. We finish the framework. And there are 5 rules to control which nodes need to be split in the backward search. The cost is shown in the table on the right. We can compare them and give the order. Also, we can see the example. The matrix is shown and the limitation is listed in the table. The imitation is generated by the backward algorithm. It requires 9 XORs. However, we observe that if we can add new candidates in the algorithm, we can find better circuits. Thus, we propose the extending bit technique. as a new candidate in our example. The new imputation is shown on the right. It only requires 8 XOR gates, but the previous circuit requires 9 XOR gates. So next question is how to use our 2 new techniques. We propose a general framework of optimization to combine these 2 techniques. Suppose that we have an imputation of linear layers generated by other heuristics. We can split the circuit into 3 parts. The first part is the base part. The second part is the target part. The third part is the unrelated part. Then we can generate a new circuit. The circuit uses the new base set and target set. There are 3 steps to generate the new circuit. First, we generate the new partial circuit. The partial circuit only contains the base set and the target set, or the base part and the target part. Next, we merge the partial circuits into the original circuit and generate new circuits. Then we need to remove redundant nodes in the new circuit. If the new circuit have fewer XOR gates, we finish the optimization. This is our algorithm to merge the circuits. By analyzing each node, we can decide which node is redundant. And another question is how to split the circuit. As the circuit size is too large, we cannot traverse all the combinations. So we use a continuous division strategy. This is our algorithm for continuous division strategy. It chooses a subset of all the combinations. Based on the strategy, we can finish the optimization in a finite time. Let's see the application of our framework. We first use the framework in the mixed columns in AES. Using the previous circuit with 103 XORs as an example, we can find the 102 XOR circuits within 5 hours. The table on shows the results of AES mixed columns in hardware. We find that the power is relevant to the area and latency. Although some imitation has fewer XOR operations, the power and latency are larger. Our imitation has smallest power and latency. Then we apply our algorithm on about 4,000 matrices giving FSE 2019. The paper has provided the corresponding circuits with a minimum depth 3. The Hamming weight for them is between 148 to 172, and the size is 32. As a result, we have improved about 3,300 matrices in terms of the number of XOR gates with the minimum depth. For each Hamming weight, we can optimize the minimum XOR gates in most cases. The minimum number of XORs is decreased from 88 to 85. Then we find a better involutory MDS matrix. It only requires 85 XORs with the depth 3. Compared with the previous work, the cost is lowest. We show the mutation on the right. Now we give a conclusion. Firstly, we give a simple conclusion. Firstly, we point out that the heuristics may have some questions. Then, we improve the heuristics of the forward search and backward search. Next, we provide the general framework of optimization. The framework can be used in any implementations and try to find better implementations. Next, we show how to apply our paper. Next week, we can use the framework to optimize existing implementations of linear layers. In the first 3 months following this presentation, we can understand our framework and try to use it with the existing heuristics. And within 6 months, we can try to propose new heuristics based on the observations of this paper and the framework. We hope the new heuristics with our framework can have a stronger effort. And finally, thanks for your attention.
All right, thank you everyone for joining the Heuristic Approaches session. Thank you to Chun Liu for his pre-recording, and thank you again to David for his speaking. Everyone have a good one.